Alcohols can be dehydrated, right? Dehydration is removal of water, obviously. So that involves removing the OH group as well as a neighboring hydrogen. So we break the CO bond to remove the OH. We break a neighboring CH bond, okay, next to it. Then we form a pi bond to make up for those bonds that we removed. Okay? That releases water, and that's a dehydration reaction. So just like our tertiary alcohols before, we can use a first order reaction with a strong acid. Okay? Acid catalyzed dehydration can happen by E1 mechanism. So let's do that. When something is acid catalyzed, let's react with acid first. Usually a pretty good rule of thumb. Something's acid catalyzed, start by protonating an oxygen or something like that. So OH group gets protonated. CH3, CH3, CH2, CH3, OH, H plus. Okay, so I have a protonated tertiary alcohol. Because it is tertiary, the protonated alcohol can leave, giving us a tertiary carbocation. Okay. And then, instead of something else attacking it, because all we did was just add acid to this, what I'm going to do is do an elimination. So let me just carefully redraw that CH2. What water will do is attack a neighboring hydrogen. The CH electrons then become the double bond to satisfy that positive charge. So our major product comes from removing a hydrogen off of the more substituted carbon. Okay? That's ch17's rule. We're going to make the most substituted alkene that we can make. A minor product might come from taking an H off one of those CH3s, but that's less common because the di-substituted product is less stable than the tri-substituted product. Okay, so that works with tertiary alcohols. Right? We protonate, make a carbocation, then water removes a neighboring proton. That's a acid catalyzed dehydration. Really only works with tertiary alcohols. We can, however, use POCl3 with pyridine. That will gently dehydrate secondary and tertiary alcohols. Primary alcohols are next to impossible to dehydrate under any kind of reasonable conditions. If I don't want to use acid, for instance, or if I have a secondary alcohol, I can pretty easily use POCl3 and pyridine. So let's draw how that works. Here's just a plain old secondary alcohol, 2-pentanol, POCl3. So P double bond O, Cl, Cl, Cl. We're going to do very similar to what happened with the tosylate. We're going to remove HCl. Right? We'll condense it. So O, P double bond O, Cl2, which is now a good leaving group, and chloride. Instead of attacking and doing SN2, chloride will do E2 with this compound. So do that. Chloride attacks the hydrogen, its electrons go in to make a double bond. That kicks out the leaving group all at once. We end up with the more substituted double bond product. Okay. So we can use forcing conditions. We can use acid to dehydrate tertiary alcohols. We can use much gentler POCl3 with pyridine. Again, pyridine helps to remove the hydrogen off of that oxygen after we did the substitution. Right there. Okay. We won't talk too much about this reaction right now. Let's wait until we have until we do our chapter on carboxylic acids and esters. But suffice it to say, if I have a carboxylic acid, I react it with an alcohol, I can do a condensation reaction. So the H is removed from the alcohol, the OH removed from the carboxylic acid, and we condense them together to make an ester. Can also do that if I have an acid chloride, C double bond O Cl. I can react with an alcohol again to make an ester, condensing this time with H and Cl. So, just have a little bit of an awareness right for that right now, but we'll save that till chapter 21.